In episode 7 of our SES course, we will discuss DeOSS, the Decentralized Object Storage Service. This video will cover what DeOSS is, why it should be used, and the workflow for interacting with DeOSS. Additionally, I will demonstrate how to use the DeOSS REST API using the command line interface. Ways of development on SES. In the coming weeks, we will cover 3 essential aspects of development on SES, providing a comprehensive understanding of the platform's potential. We'll start with the least difficult topic and gradually move to more advanced ones, ensuring a smooth and structured learning curve. Our journey begins with interacting with SES, using the Decentralized Object Storage Service, DeOSS APIs, and SDKs. This foundational aspect will help you integrate your applications with SES's decentralized storage, making data management seamless and efficient. Next, we will progress to building and deploying smart contracts, where we'll focus on creating decentralized applications, DApps, using Ink and Solidity. This will involve understanding the structure of smart contracts, deploying them on SES, and interacting with them using the Use Ink library. We'll also explore an example of an NFT marketplace, highlighting the creation and management of non-fungible tokens, a popular use case in decentralized applications. Finally, we'll tackle the most advanced topic, building custom palettes that can be integrated with SES. This section will empower you to extend the platform's functionality, providing tailored solutions that meet specific needs and use cases. Custom palettes will represent the pinnacle of customization and development within the SES ecosystem, allowing for deep integration and unique application features. Get ready to dive deep into the world of SES and unlock the potential of decentralized storage and blockchain solutions. Why develop on SES? SES comparison. In this slide, we'll explore a detailed comparison between SES, Filecoin, Arweave, and Amazon S3, focusing on key features, functionalities, and cost-effectiveness. This comparison will highlight why SES stands out as a superior choice for developers and users seeking decentralized storage solutions. Object Storage Service. SES and Amazon S3 both offer object storage services. However, SES's decentralized object storage service offers a plethora of features compared to S3, like location-based storage selection, data ownership protection, etc. We will discuss about this in more detail in this episode. In contrast, Filecoin and Arweave do not provide this feature. Decentralized Content Delivery Network. SES uniquely offers its own decentralized CDN, ensuring fast and secure content delivery. While Amazon S3 has CDN capabilities, they are centralized, unlike SES's decentralized approach. Filecoin and Arweave do not provide their own CDN services. The create, read, update, and delete operations are fully supported by SES and Amazon S3, providing comprehensive data manipulation capabilities. Filecoin supports create, read, and delete operations, while Arweave only supports create and read, limiting their data management flexibility. Location-based storage selection. SES and S3 both provide a location-based storage selection mechanism. Filecoin does not have native support, and Arweave doesn't support because their data is stored on-chain. Proof algorithm. SES employs the proof of data reduplication and recovery, PODR², with random challenges, offering a robust mechanism to ensure data integrity and security. Filecoin uses proof of replication and proof of space-time with challenge mechanisms, while Arweave utilizes succinct proof of random access. Amazon S3, being a centralized service, does not have a proof algorithm. Data ownership protection. SES provides robust ownership protection through a variety of encryption mechanisms. However, Filecoin offers comparatively weaker data ownership protection, as users are responsible for managing their own data. On the other hand, Arweave also ensures strong ownership protection by offering immutable permanent storage. In contrast, S3 is centralized and offers storage ownership protection based on a third-party provider. Disaster recovery. SES provides very high data assurance through its PODR² protocol, ensuring reliable data replication and integrity. Filecoin offers medium assurance due to reliance on single miners for replica integrity, and Arweave also provides medium assurance with on-chain storage. Amazon S3, with its centralized architecture, supports various replication mechanisms, such as cross-region replication and same-region replication, which can incur additional costs. Retrieval speed. SES has the same speed as the S3 service of Amazon, providing millisecond data access, whereas Filecoin and Arweave are relatively slow. Storage costs. SES boasts very low storage costs, ranging from $2 to $4 per terabyte per month. Filecoin also offers low storage costs, while Arweave's costs are relatively high, around $4 to $10 per terabyte per month. Amazon S3, of course, is the most expensive, with costs between $21 and $24 per terabyte per month. Payment rules. In SES, users pay only for renting the storage space with no retrieval fees. Filecoin charges for both storage and retrieval, while Arweave, like SES, only charges for storage, with retrieval being free. Amazon S3 charges for both storage and retrieval, adding to the overall cost. The last recorded storage capacity of the SES and testnet was more than 45 petabytes. Filecoin boasts a substantial capacity of nearly 6 exabytes, while Arweave has a capacity of around 200 petabytes. For Amazon S3, capacity details are not publicly disclosed due to its centralized nature. As of 4 September, the SES testnet recorded more than 6,000 storage nodes, demonstrating a robust and distributed network. Filecoin's mainnet has around 2,200 nodes, and Arweave operates with around 300 plus nodes. The number of nodes for Amazon S3 is unavailable, as it is a centralized service. This comparison underscores the unique strengths of SES, particularly in offering a decentralized CDN, comprehensive CRUD operations, low-cost storage, and robust proof algorithms, making it a compelling choice for decentralized application development. DeOSS stands for Decentralized Object Storage Service. It simplifies storage services for developers and offers HTTP APIs for object-based storage service that is low-cost, secure, and highly scalable, making it the ideal solution for handling unstructured data. DeOSS actually serves as a gateway to the SES network, which uses blockchain-based distributed storage protocols. It serves as a Web3 platform catering to developers, offering capabilities comparable to a centralized AWS S3. You can say DeOSS is the next generation S3 or Google Cloud of Web3. It is the fast data access portal of the SES network, designed to provide low latency and high throughput. DeOSS offers a convenient platform for application development, authorization management, and custom development capabilities, and most importantly, ensures that data ownership remains with the user. So why DeOSS? DeOSS provides a comprehensive suite of features, making it an attractive choice for a broad range of applications. It provides comprehensive HTTP APIs and SDKs, which makes integration effortless. One of the standout features of DeOSS is its location-based distributed storage, which provides data storage and access based on geographical locations. It is designed to be highly scalable. It provides lightning-fast data access similar to Web 2. It also provides robust mechanisms for data authorization and access control, ensuring that sensitive information remains protected. You can store a wide range of data, for example, NFTs, digital assets, backups, images, videos, and so on. With DeOSS, you can guarantee users retain complete ownership and sovereignty of their data, free from potential risks which are associated with centralized and third-party storage solutions. Lastly, it is also IPFS compatible. DeOSS system architecture. In the DeOSS system architecture, we find a high degree of integration with the SES blockchain at its core, setting it apart from traditional distributed system architectures. This unique blend creates an open and decentralized object storage system that seamlessly connects the interface layer and service layer. The interface layer provides rich and user-friendly interaction interfaces, while the service layer offers highly scalable and customizable object storage services. DeOSS serves as the gateway to the SES network, enabling smooth data flow between applications and the underlying storage infrastructure. It achieves this by providing various applications with data access interactions interfaces at the top, while tightly integrating with the storage node network and SES blockchain at the bottom. The interface layer is primarily composed of RESTful HTTP APIs designed to simplify user interactions. To enhance developer accessibility, SES has implemented SDKs in Golang, JavaScript, and Rust. This layer enables users or applications to perform essential operations such as uploading, downloading, and deleting files, querying file status, managing storage space, and handling buckets. These tasks are streamlined, requiring only a few simple parameters, making it easy to access decentralized object storage services. Moving on to the service layer. This segment of DeOSS includes several functional modules like the data processing module, data scheduling module, peer-to-peer communication module, and the SES chain client. When a file is transmitted from the application layer, it undergoes pre-processing, which includes data encryption, segmentation, sharding, and redundancy. The data scheduling module then randomly distributes these fragments to nearby storage nodes. The data storage orders and metadata are subsequently preserved on the SES blockchain through the client. During data retrieval, the system first queries the file metadata from the blockchain. It then collects sufficient file fragments from the corresponding storage nodes, assembles them, decrypts the data, and returns the complete file to the application layer. This comprehensive process ensures that data integrity and security are maintained throughout. DeOSS also plays a pivotal role in the SES content distribution and edge networks, managing data caching and distribution tasks. You can think of DeOSS as the cache and retrieval node currently implemented together within the system. However, in future releases, these functionalities will be split into separate nodes, enhancing scalability and performance. When a user or application initiates a download, DeOSS first checks for a local cache hit. If the data isn't available locally, it then requests the data from nearby peer nodes, or, as a last resort, retrieves it from the storage nodes. All uploaded or downloaded data is cached to facilitate quicker response times for future requests. As multiple DeOSS instances collaborate, they form an extensive cache network, eliminating data silos and ensuring seamless data sharing globally. Additionally, DeOSS stands out as a highly extensible and customizable component within the SES ecosystem. Developers can tailor its functionality by enabling or disabling caching, setting access whitelists or blacklists, and configuring the system to serve specific storage node clusters. Furthermore, DeOSS allows for secondary development, enabling the creation of unique high-security custom services tailored to specific needs. The SES team supports this with a suite of modular developer tools, making it easier for developers to implement their desired business logic and expand the system's capabilities. This architecture not only ensures efficient data storage and retrieval, but also provides robust support for a wide range of applications, making DeOSS a powerful tool in the SES ecosystem. Let's explore how this architecture supports the decentralized storage services that SES offers and benefits that it brings to its users and developers alike. Data Access Process, DeOSS Workflow. Now let's dive into the workflow to understand how to navigate and leverage DeOSS, which is crucial for unlocking its full potential. Let's break down the workflow into two key steps. Step 1. Depositing SES tokens. The first thing that we need to do is get some SES tokens, as these tokens are the key to unlock the vast potential of DeOSS. Step 2. Purchasing space and authorizing the gateway. Purchasing space can either be done from the SES Explorer or using the APIs and SDKs. The easiest way is to use the SES Explorer to purchase space. The amount of space that can be purchased is in gigabytes, and the price we pay is based on gigabytes per 30 days. This may vary on the mainnet. We can also extend the validity of our purchase space from the Explorer. Authorizing the gateway is necessary for the gateway to perform some operations on the user's behalf, such as uploading or downloading file segments, renewing or expanding space, and other storage operations. After purchasing the required storage space and authorizing DeOSS, we can start with performing storage operations using the APIs and SDKs. When users upload a file, the gateway submits transactions on the user's behalf, streamlining the process and ensuring that our storage-related information is written on the blockchain. Also, the gateway distributes file segments strategically to storage miners behind the scenes. The SES chain then challenges storage miners periodically, for which miners have to prove data integrity by submitting storage proofs back to the chain. So, this is the overview of the workflow of DeOSS. In the next video, we will set up our account and learn how to use the DeOSS REST API to upload and download files. Moving on to data access process for the file upload. The file upload can be split into multiple steps, starting from resumable chunk upload. Chunked resumable upload ensures reliable file uploads even in unstable network conditions. When users upload files, the process begins by transferring the files to DeOSS, which then acts as a proxy to handle the processing and distribution. Given that the data files can be quite large and network stability can vary, SES offers a chunked resumable upload file. This feature provides a robust solution for maintaining the stability of data transmission. Here's how it works. Using the provided SDK, the upload file is divided into chunks of specific sizes according to the network conditions. When the network connection is strong, the data is divided into larger chunks. When the connection is weak, it is divided into smaller chunks. This adaptive chunking ensures efficient and reliable data transmission. These data chunks are then uploaded to DeOSS, supporting out-of-order and concurrent uploads. This means that the chunks don't need to be uploaded sequentially, and multiple chunks can be uploaded at the same time. This optimizes the upload process. As DeOSS successfully retrieves each chunk, it returns the index of that chunk to the application. If a chunk fails to upload or if the connection times out, DeOSS sends an error message. The application can then retry uploading the failed chunk, ensuring that no data is lost. Once all chunks have been successfully uploaded, DeOSS returns a unique index hash to the user, confirming that the file upload has been completed. The user's file is then stored in the DeOSS cache queue, where it awaits pre-processing. This pre-processing includes tasks like data encryption and segmentation. Finally, the processed data is distributed to a group of storage nodes for persistent storage, ensuring the data is securely stored and easily accessible. The next step is data processing. When a file is uploaded in chunks, DeOSS first reassembles the uploaded chunks into a complete file. This file is then divided into segments, each adhering to a predefined specification, with each segment being 32 MIBs in size. Following this, DeOSS processes each segment separately by slicing them and adding redundancy. Specifically, each 32 MB segment is divided into 12 smaller fragments, each of 8 megabytes, thereby ensuring that redundancy is built into the data structures. The segment size may vary on the mainnet. These 12 fragments are then rearranged and used to calculate a unique file ID or FID, which uniquely identifies the stored file. The metadata associated with the data, such as its size, name, and number of segments, and the number of fragments, is uploaded to the SES chain. This metadata forms what we refer to as a storage order, essentially logging all essential details about the file on the blockchain, ensuring a transparent and traceable record of the stored data. After this pre-processing, the user's data is expanded to approximately 3 times its original size. This redundancy is a crucial aspect of the system as it ensures data resilience. Even if 2 out of the 3 of the data fragments are lost, the original file can still be reconstructed and downloaded without loss. This robust mechanism guarantees high data availability and reliability. Moreover, users have the option to encrypt their data during this process. This adds an additional layer of security, protecting the privacy and confidentiality of the stored information. This comprehensive data processing workflow not only ensures that data is securely stored and easily retrievable, but also that it remains private and protected, offering users peace of mind in using DeOSS for their storage needs. The third step is data distribution. After the data has been processed and divided into fragments, DeOSS employs a scheduling module to randomly distribute these fragments to various storage nodes for persistent storage. This random distribution is a crucial aspect as it mitigates the risks associated with central storage, ensuring data security and resilience. Developers have the flexibility to customize the scheduling strategies via configuration files, allowing them to prioritize or avoid certain storage nodes based on their specific requirements. However, it is imperative that the fragments are stored in a distributed manner to maintain data integrity and security. The scheduling model is designed to select storage nodes that exhibit good communication status and high service quality. This selection criterion ensures that the data fragments are stored on reliable nodes, facilitating efficient and dependable data access. Once the fragments are successfully dispatched, storage nodes must report back to the SES chain, confirming the successful receipt of the storage data. This reporting mechanism allows DeOSS to properly receive feedback on the storage status. In this case, where a storage node fails to report back to us with a reasonable time frame after receiving its file fragments, DeOSS takes the corrective action. The file system will attempt to reassign the fragments to a new, more reliable nodes, ensuring the continuity of data storage. Additionally, nodes that consistently fail to report will be flagged, and if they exceed a certain threshold of failures, they will be placed in a cooldown pool. Nodes in this pool will be temporarily barred from receiving further data transmissions, effectively penalizing uncooperative behavior. Storage nodes that are not proactive in receiving and storing user files will face consequences. They risk losing the trust of DeOSS instances across the network, making it challenging for them to acquire new user data and expand their service there. This lack of trust and reduced data storage opportunities can directly impact their earnings, providing a strong incentive for nodes to maintain high standards of reliability and communication. This data distribution process not only ensures that data is stored securely and efficiently, but also fosters a trustworthy and robust network of storage nodes within the SES ecosystem. Now let's discuss the DeOSS file download process. When a user initiates a file download, DeOSS first checks its local cache to see if the requested file is available. This step is designed to optimize the retrieval process by providing immediate access. The file is already cached. If the file isn't found in your local cache, DeOSS proceeds to the next step, querying the on-chain file metadata. This metadata contains vital information about the storage node location of the data fragments, allowing DeOSS to efficiently locate the necessary parts of the file. Once the storage locations are identified, DeOSS downloads the required data fragments from the corresponding storage nodes. Remarkably, only 1/3 of the total fragments need to be retrieved to reconstruct the complete file. This capability is a result of the redundancy and data distribution mechanisms in place, ensuring that the file can be fully restored even with partial data availability. In addition to direct downloads from storage nodes, DeOSS enhances the data access process through the use of a peer-to-peer network. This network facilitates data sharing with nearby cache nodes or other DeOSS instances, enabling high-speed downloads. The peer-to-peer network adds another layer of efficiency, allowing users to access data from multiple sources, which can significantly speed up the download process. A notable feature of DeOSS is its unique upload once, download anywhere functionality. This means that users and applications can download data from any DeOSS instance regardless of which DeOSS the data was initially uploaded to. This feature provides flexibility and convenience as it eliminates the need to use the same node for both upload and download, thereby enhancing the accessibility and availability of data across the network. File merging. When DeOSS retrieves data fragments from various sources, be it a storage node, cache node, or another peer DeOSS instance, it uses the Reed-Solomon algorithm to reconstruct the complete data segments. This reconstruction process is guided by the file metadata, which provides the necessary information for accurately assembling the data. Once the data segments are restored, DeOSS merges them in the correct sequence to form the complete file. This file merging process effectively reverses the earlier file pre-processing steps, ensuring that the data is fully and accurately restored for user access. Encryption and decryption. DeOSS supports encryption and decryption to protect user files. Currently, the system utilizes AES symmetric encryption with plans to incorporate additional encryption methods, such as proxy re-encryption in future updates. The encryption process begins during the file preprocessing stage. After the file is segmented, each segment undergoes symmetric encryption, ensuring that the data is secure before it is stored in the network. During the file merging, the decryption process takes place. DeOSS starts by restoring the encrypted fragments back to their respective segments. It then decrypts each segment and merges them into the original unencrypted user file. This process ensures that user data remains secure during storage and is accurately and safely restored upon retrieval. These robust processes of file merging and encryption/decryption ensure that data integrity and security are maintained within the SES network. This offers users peace of mind regarding the safety of their stored data. Now let's talk about the DeOSS SDK. The SES ecosystem provides developers with powerful tools to seamlessly integrate DeOSS and decentralized storage into their applications. We support SDKs in Rust, Golang, and JavaScript, giving developers the flexibility to work in the languages they are most comfortable with. Additionally, our DeOSS RESTful API ensures easy access and integration with the SES network, allowing for streamlined development and integration processes. Whether you're building in Rust, Golang, JavaScript, or using our RESTful API, the DeOSS SDK makes it easy to leverage the full potential of decentralized storage on the SES network. So in this video, we've covered enough theory. In the next video, we will learn how to use the DeOSS REST API to upload and download files. Thank you for watching, and be sure to join our community by scanning the QR code.